Welcome friends. In this session, we will discuss the topic analysis of algorithms. An algorithm is a step-by-step specification on how to perform a certain task, and the time complexity is the time it takes to execute an algorithm. We have come across the class of solvable or computable problems and unsolvable problems. We attempt to separate the practically solvable problems from those that cannot be solved in a reasonable time. When constructing a computer algorithm, it is important to assess how expensive the algorithm is in terms of storage and time. Algorithm complexity analysis tells how much time does an algorithm takes to solve a problem. The size of a problem instance is typically measured by the size of the input that describes the given instance. Algorithm complexity analysis is based on counting primitive operations such as arithmetic, logical, reads, writes, data retrieval, data storage, etc. Time an expresses the time complexity of algorithm A and is defined as the greatest number of primitive operations that could be performed by the algorithm given a problem instance of size n. We are usually more interested in the rate of growth of time A than in the actual number of operations in the algorithm. Thus, to determine whether it is practical or feasible to implement A, we require a not too large upper bound for time an. Time complexity of algorithms is expressed using the big O notation. The complexity of a function f of n is big O of g of n if modulus of f of n is less than or equal to c into modulus of g of n for all n greater than 0 and some constant c. Let f and g be functions on n, then f of n is equal to big O of g n means that f is of the order of g, that is f grows at the same rate of g or slower. F of n is equal to omega of g of n means that f grows faster than g. F of n is equal to theta of g of n means that f and g grow at the same rate. An algorithm is said to perform in polynomial time if and only if its time complexity function is given by O of n raised to k for some k greater than or equal to 0. That is, an algorithm A is polynomial time if time A of n is less than or equal to f of n and f is a polynomial, that is, f has the form a1 n raised to k plus a2 n raised to k minus 1 plus etc. plus am. Example 1. 3x square plus 2x plus 2 is equal to O of x square because 3x square plus 2x plus 2 is less than or equal to 5x square for x greater than 1 and 3x square plus 2x plus 2 is less than or equal to 7x square for x greater than 0. We say that f is equivalent to g if f is equal to O of g and g is equal to O of f. Example 2. X square is equal to O of 3x square plus 2x plus 2 because x square is less than or equal to 3x square plus 2x plus 2 for x greater than or equal to 0. Then we could say that 3x square plus 2x plus 2 is equivalent to x square. An algorithm is said to perform in exponential time if its complexity function is not bounded by a polynomial but instead is given by O of c raised to n for some c greater than 1. Comparing algorithms. Let two algorithms A and B for solving a problem P and let time A and time B be the time complexities of the algorithms A and B respectively. Algorithm A is said to have the same complexity as algorithm B in solving the problem P if time A is equivalent to time B. Algorithm A is said to be better than algorithm B in solving P if time A is O of time B but time B is not O of time A. A problem P is said to be tractable if there is a known polynomial time algorithm to solve it. A problem P is said to be intractable if it is solvable but there is not known polynomial time algorithm to solve it. Example 3. Determine the time complexity of the binary addition. Solution. Suppose two binary numbers with n digits a equal to an minus 1 and an minus 2 etc. a naught and b equal to bn minus 1, bn minus 2, etc. b naught. Then the sum is given by a plus b is equal to d, which is equal to dn, dn minus 1, dn minus 2, etc. d naught. Each di is obtained by adding and carrying in the usual way. Di is equal to ai plus bi plus ci mod 2, where ci minus 1 is the carry from the previous sum. It is impossible to calculate all the di in parallel because of the carry. Each di must await its turn in the order of computation. Therefore, the complexity of the standard binary addition algorithm is O of n. The class P. Given the decision TSP, that is the travelling salesman problem, for a set of n cities, say C equal to set C1, C2, etc. Cn, and a distance between each pair of cities Ci and Cj given by Dij, which is an element of Z plus. Is there a tour of all cities starting and ending in the city C1 and visiting each city exactly once, such that the total distance travelled is less than or equal to b? The number of possible tours is n minus 1 factorial. A deterministic machine would be able to explore only one tour at a time, so it would take exponential time to solve the decision TSP. There is no known deterministic machine that can solve the decision TSP in polynomial time. Let M be a deterministic Turing machine and input x element of sigma star. The time complexity time m of a deterministic Turing machine M is given by time m of n is equal to maximum of the set M such that there is an x element of sigma star such that the computation of M on input x is of length m. If time m of n is O of n raised to k for some k greater than or equal to 0, then M is said to take polynomial time. The Turing machine M is an algorithm if halts for all inputs and then time m of n is defined for all n. Then the class P is defined as the class of problems which can be solved by polynomial time deterministic algorithms. Problems in P can be solved quickly. P is the set of all L such that there is a polynomial time deterministic Turing machine which accepts L. The class NP. For the decision TSP which we have discussed, a non-deterministic machine with unlimited parallelism would be able to solve the decision TSP in polynomial time. Let NDTM be a non-deterministic Turing machine and input x element of sigma star. There is at least one computation sequence, possibly more, by which NDM accepts x. The time taken by NDTM to accept x is given by the length of the shortest of the computation sequences by which NDTM accepts x. The time complexity time NDM of a non-deterministic Turing machine NDTM is given by time NDM of n is equal to 1 if no inputs on length n are accepted by NDTM, and time NDM of n is equal to the minimum of the set M such that there is an x element of sigma star such that the time taken by NDTM to accept x is m. Otherwise, we say that NDTM is polynomial time if and only if time MDM of n is O of n raised to k for some k greater than 0. Then the class NP is defined as the class of problems which can be solved by polynomial time non-deterministic algorithms. Problems in NP can be verified quickly. That is, NP is equal to the set L such that there is a polynomial time non-deterministic Turing machine which accepts L. It should be clear that P is a subset of NP. It is widely believed that P is not equal to NP, but this has not been formally proven. NP complete problems arise in many domains like Boolean logic, graphs, sets and partitions, sequencing, scheduling, allocation, automata and language theory, network design, compilers, program optimization, hardware design and optimization, number theory, algebra, etc. The class NP complete. Then within the class NP there are easy problems, those in P, and very much harder problems called NP complete problems. So in the figure you can see two subsets of class NP which are class NP complete and class P. Intuitively, the class NP complete are the hardest problems in NP as defined by Cook's theorem. More formally, problem P is NP complete if P is an element of NP and for any P dash element of NP, P is equivalent to P. Assume two problems P1 and P2 and an algorithm A to solve P2. If each instance of P1 can be easily, that is in polynomial time, transformed to some instance of P2, then we could use algorithm A to solve P1. Theorem 1. If P1 is equivalent to P2, respectively L1 equivalent to L2 and P2 is an element of P and P1 is an element of P, two problems P1 and P2 respectively L1 and L2 are polynomially equivalent if P1 is equivalent to P2 and also P2 is equivalent to P1. Respectively, L1 is equivalent to L2 and L2 is equivalent to L1. All evidence so far is that P is an element of NP, so it seems that no NP complete problem has a known polynomial time algorithm to solve it. Theorem 2. If P1 is NP complete and P2 is an element of NP, then P1 is equivalent to P2 implies that P2 is also NP complete. The first problem known to be NP complete was the satisfiability of a set of clauses or SAT problem. The proof was given by Cook in 1971. The proof shows first that SAT problem is an element of NP and then it shows that for all P dash element of NP, then P dash is equivalent to SAT. The class NPI. Accepting that P is not equal to NP does not mean necessarily that P union NP complete is equal to NP. Some problems might not be in P, neither in NP complete. It has been shown that if P equal to NP, then NPI is equal to NP minus P union NP complete. However, the vast majority of practical problems are in P or in NP complete. You can see the figure. The class NP has subsets now, class NP complete, class NPI and class P. Example 4. It is a conjecture that the decision problems like graph isomorphism and composite number are both in NPI. Graph isomorphism problem. Given two graphs G1 and G2, is G1 isomorphic to G2? For the special case of G1, G2 being planar, the problem is solved in polynomial time. But no polynomial time algorithm has been found to solve the general case, and no one has been able to prove that graph isomorphism is NP complete. Composite number problem. Given a positive integer k, are there integer m and n greater than 1 such that k is equal to m into n? If any polynomial time algorithm can be designed to test primality, then the problem would be in P, but such an algorithm has not been found. However, there is a polynomial time algorithm for solving the composite number problem when k is not a prime number. Now we move on to discrete numeric functions. A class of function whose domain is the set of natural numbers and whose range is the set of real numbers is referred to as discrete numeric functions or briefly numeric functions. In other words, a discrete numeric function is a function from the set 0, 1, 2, 3, etc. into the set R of real numbers. For a numeric function A, we use A0, A1, A2, etc., An, etc. to denote the values of the function at 0, 1, 2, 3, etc., n, etc. Thus, AR is the value of the numeric function at R. Let us see some examples of numeric functions. Example 1. A is equal to 8n cube plus 1 for n greater than or equal to 0. Second one, Bn is equal to 3 raised to n for 0 less than or equal to n less than or equal to 11 and 2 raised to n minus 1 for n greater than or equal to 12. Third one, Cr is equal to minus 8 for 0 less than or equal to r less than or equal to 4 and 3 raised to r for r greater than or equal to 5. These three gives the concise specification of numeric functions. Example 2. Suppose we deposit rupees 10,000 in a saving account at an interest rate of 7% per year compounded annually. The total amount in the account at the end of each year can be described by a numeric function A. AR is equal to 10,000 into 1.07 raised to r for r greater than or equal to 0. Manipulation of numeric functions. The sum of two numeric functions is a numeric function whose value at r is equal to the sum of the values of two numeric functions at r. That is, the sum of two numeric functions ar and br is a numeric function cr whose value at r is equal to the sum of the value of ar and br at r. The product of two numeric functions is a numeric function whose value at r is equal to the product of the values of the numeric functions at r. Example 3. Let two numeric functions a and b be given by ar is equal to 0 for 0 less than or equal to r less than or equal to 3 and 3 raised to minus r plus 7 for r greater than or equal to 4. br is equal to 3 minus 2 raised to r for 0 less than or equal to r less than or equal to 2 and r plus 5 for r greater than or equal to 3. Obtain a plus b and a into b. Solution. Let C be the sum of two functions a and b, then CR is equal to AR plus BR, which is given by 3 minus 2 raised to r for 0 less than or equal to r less than or equal to 2, 8 for r equal to 3 and 3 raised to r plus 12 for r greater than or equal to 4. Let D be the product of the two functions a and b, then dr is equal to AR into BR, which is equal to 0 for 0 less than or equal to r less than or equal to 3 and 3 raised to minus r plus 7 into r plus 5 for r greater than or equal to 4, which is equal to 0 for 0 less than or equal to r less than or equal to 3 and r into 3 raised to minus r plus 5 into 3 raised to minus r plus 7r plus 35 for r greater than or equal to 4. Scaled version. Let a be a numeric function and k be a real number. We use Ka to denote the numeric function whose value at r is equal to k times ar. The numeric function Ka is called the scaled version of a with scaling factor k. Modulus of a numeric function. Let a be a numeric function, then modulus of a denoted by mod a is a numeric function defined as mod a is equal to ar if ar is non-negative and minus of ar if ar is negative. Definition of s raised to ia and s raised to minus ia for a numeric function. Let a be a numeric function and I be a positive integer. We use s raised to ia to denote a numeric function such that its value at r is 0 for r equal to 0, 1, 2, 3 etc. I minus 1 and is a r minus I for r greater than or equal to I. S raised to minus ia is also a numeric function such that s raised to minus ia is equal to a of r plus I. Accumulated sum. The accumulated sum of a numeric function a is a numeric function whose value at r is equal to summation I equal to 0 to r ai. Forward and backward difference. The forward and backward difference of a numeric function a is a numeric function denoted by delta a and del a respectively, whose value at r is delta a is equal to ar plus 1 minus ar and del a is equal to ar minus 1 at r greater than or equal to 1 and 0 at r equal to 0. Example 5. Let a be a numeric function such that ar is equal to 0 for 0 less than or equal to r less than or equal to 2 and 2 raised to minus r plus 5 for r greater than or equal to 3. Find the value of delta a and del a. Solution. Let b equal to delta a be the forward difference, then br is equal to delta a is given by 0 for 0 less than or equal to r less than or equal to 1, 41 by 8 for r equal to 2, minus 2 raised to minus of r plus 1 minus 2 raised to minus r for r greater than or equal to 3. Let c equal to del a be the backward difference of a, then cr is equal to 0 for 0 less than or equal to r less than or equal to 2, 41 by 8 for r equal to 3 and minus 2 raised to minus r for r greater than or equal to 4. Convolution of two numeric functions. Let a and b be two numeric functions. The convolution of a and b denoted by a star b is a numeric function such that Cn is equal to a dot bn plus a1 bn minus 1 plus etc. an b dot, which is equal to summation I equal to 0 to n ai bn minus I. Next is asymptotic behavior of numeric functions. Let a and b be numeric functions. We say that a asymptotically dominates b or b is asymptotically dominated by a if there exist a positive constants k and m such that mod Br is less than or equal to m into Ar for r greater than or equal to k. Intuitively, that A asymptotically dominates B means that A grows faster than B. Thus, for sufficiently large r, the absolute value of Br does not exceed a fixed proportion of Ar. For any numeric function A, modulus A asymptotically dominates A. For a given discrete numeric function A, let O of A denote the set of all numeric functions that are asymptotically dominated by A. Then O of A is read as order of A or big O of A. For any numeric function A is an element of order of A. If B is an element of order of A, then for any constant alpha, alpha into B is an element of order of A. For any integer I, s raised to ib is an element of order of s raised to ia. If both B and C belongs to order of A, then for any constant alpha and beta, alpha into B plus beta into C belongs to order of A. If C belongs to order of B and B belongs to order of A, then C belongs to order of A. It is possible that A belongs to order of B, then B belongs to order of A. It is also possible that A is not an element of order of B and B is not an element of order of A. It is possible that C is in both order of A and order of B, while A is not in order of B and B is not in order of A. Example, let A equal to A0 plus A1r plus A2r square plus etc. an r raised to n, then A is equal to order of r raised to n. Since modulus of A0 plus A1r plus etc. plus an r raised to n is less than or equal to mod A0 plus mod A1 into r plus mod A2 into r square plus etc. plus mod an into r raised to n, that is less than or equal to mod A0 plus mod A1 plus etc. plus mod an into r raised to n, that is less than or equal to some m into r raised to n, that is A is asymptotically dominated by r raised to n. Next example, order of 1 is a subset of order of log r, which is a subset of order of r, subset of order of r raised to I, subset of order of k raised to r, which is a subset of order of r factorial. Let A and B be two sets of numeric functions. We define A plus B as the set A plus B such that A belongs to A and B belongs to set B. And alpha into A is equal to the set alpha into A where A is an element of set A. And A into B is equal to the set AB where A belongs to the set A and B belongs to the set B. If B belongs to order of A and order of B is a subset of order of A, consequently if B belongs to order of A and A belongs to order of B, then the sets order of A and order of B are equal. For any A, order of A plus order of A is equal to order of A. And if B belongs to order of A, then order of A plus order of B is equal to order of A. For any constant alpha, alpha into order of A is equal to order of alpha A, which is equal to order of A. For any A and B, order of A into order of B is equal to order of AB. Example, let A equal to 3r cube plus 2r square plus r, then A is order of r cube or 3r cube plus order of r square or 3r cube plus 2r square plus order of r. Note that 3r cube plus 2r square plus order of r, which is a subset of 3r cube plus order of r square, in turn it is a subset of order of r cube. Next example, let A equal to r plus order of 1 by r and B is equal to root r plus order of 1 by root r. We have A into B is equal to r raised to 3 by 2 plus order of root r. For a given numeric function A, let omega A denote the set of all numeric functions B such that there exist positive constants k and m with mod Br is greater than or equal to MAR for r greater than or equal to k. In other words, if B is in omega A, then B grows at least as fast as A. For a numeric function A, let theta A denote the set of all numeric functions B such that there exist positive constants m, m dash and k with MAR less than or equal to mod Br less than or equal to m dash AR for r greater than or equal to k. In other words, if B is in theta A, then B grows as the same rate as A. Generating functions. For a numeric function A is equal to A0, A1, A2, etc., AR, etc., we define an infinite series A0 plus A1z plus A2z square plus etc. plus ARz raised to R plus etc., which is called the generating function of the numeric function A. For example, here are some sequences and their generating functions. The sequence 0, 0, 0, the corresponding generating function is 0 plus 0 into z plus 0 into z square plus etc., which is equal to 0. Second one, the sequence 1, 0, 0, the generating function is 1 plus 0 into z plus 0 into z square plus etc., which is equal to 1. Third one, the sequence 2, 3, 1, 0, etc., the generating function is 2 plus 3 into z plus 1 into z square plus 0 into z cube plus etc., which is equal to 2 plus 3z plus z square. In general, the sequence an has the generating function a of z is equal to 1 plus a into z plus a square into z square plus etc., which is equal to summation k equal to 0 to infinity a raised to k z raised to k, which is equal to 1 by 1 minus a z. Therefore, a generating function in which the coefficients of z raised to n are the terms of the sequence A is called binomial generating function of the sequence A. Let h of z be a generating function for a sequence A as follows. H of z is equal to a0 plus a1z plus a2 z square by 2 factorial plus a3 z cube by 3 factorial plus etc., which is equal to the summation n equal to 0 to infinity a n into z raised to n by n factorial. This series is exponential. The generating function h of z defined for a sequence A is equal to a0, a1, a2, etc. is called exponential generating function. If a of z is the generating function for A, then the generating function for the accumulated sum summation I equal to 0 to r ai is 1 by 1 minus z into a of z. Consider the numeric function A such that AR is equal to C of NR for some fixed n. The generating function of A is A of z is equal to Cn0 plus Cn1 into z plus etc. Cnr into z raised to r plus etc. Cnn into z raised to n, which is equal to 1 plus z the whole raised to r. Operations on generating functions. Scaling. If for the sequence A dot A1, A2, etc., the generating function is A of z, then for the sequence C into A0, C, A1, etc., the generating function is C into A of z. Addition. If the sequence A0, A1, A2, etc., is having the generating function A of z and the sequence B0, B1, B2, etc., is having the generating function Bz, then the sequence A0 plus B0, A1 plus B1, etc., is having the generating function A of z plus B of z. Right shifting. If the sequence A0, A1, A2, etc., is having the generating function A of z, then the sequence 0, 0, 0, etc., 0, A0, A1, A2, etc., is having the generating function z raised to k into A of z for k leading zeros. Differentiation. If the sequence A0, A1, A2, etc., is having the generating function A of z, then the sequence A1, 2A2, 3A3, etc., is having the generating function A dash z. Product. If the sequence A0, A1, A2, etc., is having the generating function A of z and sequence B0, B1, B2, etc., is having the generating function B of z, then the sequence C0, C1, C2, etc., is having the generating function Az into Bz, where C is A star B, that is Cr is equal to A0 Br plus A1 Br minus 1 plus A2 Br minus 2 plus etc. plus Ar minus 1 B1 plus Ar B0. Note: if A of z and B of z are generating functions for the sequences A and B respectively, then A of z star B of z is not the generating function of A star B. Example: let AR denote the number of ways of selecting R objects from n objects with unlimited repetitions. Since each object can be selected as many times as we wish, AR is equal to the coefficient of z raised to r in the expansion of 1 plus z square plus etc. the whole raised to n. Solution. since 1 plus z plus etc. the whole raised to n is equal to 1 minus z the whole raised to minus n, we obtain AR as minus 1 raised to r into minus n minus 1 etc. into minus n minus r plus 1 by r factorial, which is equal to n plus r minus 1 factorial by r factorial into n minus 1 factorial, which is C of n plus r minus 1 r. Before we conclude this session, let us summarize what we have learned. We began the session with analysis of algorithms. We saw the time complexity of algorithms with examples. We also saw a classification of problems based on its complexity. We continued our discussion with discrete numeric functions and considered several examples. We saw various operations on numeric functions and the asymptotic behavior of numeric functions. Then we moved on to generating functions and saw various operations on generating functions. The following problems are given for a better understanding of the topics. First one, show that f and g have the same order for f of n is equal to 5n square plus 4n plus 3 and g of n is equal to n square plus 100n. Second one, determine the least integer n such that f of x is equal to 3x cube plus x square log x is theta of x raised to n. Third one, determine the numeric functions corresponding to the generating functions a 1 by 1 minus z cube, b 1 plus z the whole raised to n plus 1 minus z the whole raised to n, c 1 by z square minus 6z plus 5. Here are some books for further reading. First one is Element of Discrete Mathematics, 2nd edition by C.L. Liu, by McGraw-Hill International Edition, Computer Science Series 1986. Second one is Discrete Mathematics and its Application, 6th edition by Kenneth H. Rosen, by McGraw-Hill International Edition. Third one, Concrete Mathematics by R. L. Graham, D. E. Nath and O. Patashnik, by Addison Wesley. Thank you for watching this session. See you next time. Till then, goodbye.